December 2nd, 1942. World War II is raging across the globe, and we are just days away from the anniversary of America's entry into the conflict. At Harvard, James Conant sits in his office as university director when the telephone rings. On the other end, physicist Arthur Compton delivers a simple coded message. The Italian navigator has landed in the New World. This cryptic communication informs Conant of a successful secret project. In Chicago, Enrico Fermi and his team have just achieved a sustained nuclear chain reaction inside the CP-1 pile, their first functioning nuclear reactor, the culmination of a decade of research, opening the door to the next phase, the atomic bomb. 10 years earlier, in 1932, James Chadwick discovers the neutron, a particle with no electrical charge. Immediately, the scientific community realizes such a particle could prove extremely valuable. Unlike protons or electrons, it can interact with atomic nuclei without being repelled by electrical charges. This leads Enrico Fermi to begin bombarding every element in the periodic table with neutrons. When he bombards uranium, the heaviest naturally occurring element, he encounters deeply strange results. Unable to interpret them, he shares his findings with colleagues. By the end of 1938, German scientists Otto Hahn and Fritz Strassmann discover that when uranium absorbs a neutron, its nucleus becomes unstable and rapidly splits into two other elements, not always the same ones. They name this phenomenon nuclear fission. A few months later, Frédéric Joliot's French team discovers that during this fission, an average of 3 new neutrons are released. And that is when it clicks. If bombarding one atom with a neutron produces 3 more neutrons plus enormous energy, you could create a chain reaction. By spring 1939, secret patents are filed detailing concepts for nuclear reactors and atomic bombs. But then war arrives, strangling communication within the scientific community. Research continues on one side in Germany, on the other in the United States, and you know how that ended. Thus was born the first chain reaction. After 4.5 billion years of Earth's history, a species of primate had piled enough uranium in one place to generate energy, to create, and to destroy. At least that's what we believed for 30 years. Then we discovered that other living beings had done this before us. Long before us. Long before even the appearance of dinosaurs. Today, I'm going to tell you about the discovery of the Oklo nuclear reactors, not crafted by human hands, and how they allowed us to identify the oldest known animals in Earth's history. We are now in June 1972 at Pierre-Latte, France. Here stands a facility processing uranium hexafluoride, enriching it for France's military needs. I will explain what that means in a moment. For now, what matters is that at the enrichment cycle entrance, a routine test is performed on a sample, mass spectrometry, an analysis that precisely determines a sample's composition. On this particular day, the sample shows an anomaly. Normally, it displays a uranium-235 rate of 0.72%. But today, the rate measures only 0.7171%. This difference seems ridiculous, yet it is enormous, and it will trigger an investigation by the French Atomic Energy Commission. Let me explain why. Throughout the universe, all chemical elements are forged in the hearts of stars through hydrogen fusion, creating progressively heavier elements. Fusing atomic nuclei releases energy. That is stellar fuel. But this only holds true for elements lighter than iron. Starting with iron, fusion no longer releases energy. It absorbs it. When a star begins manufacturing iron, its core, previously its engine, stalls, and collapses under gravity. Upon reaching critical density, it explodes. These are supernovas. During this tremendous explosion, which can shine as bright as an entire galaxy, the quantity of energy released enables the formation of atoms heavier than iron. Before our sun existed, generations of stars were born and died, dispersing heavier elements during their explosions. Our sun and the entire solar system were born from the accretion of a gas cloud that contained heavy elements from a nearby supernova explosion. That supernova created, among other things, uranium. Uranium is an unstable chemical element. Given sufficient time, it will spontaneously decay into something else, ultimately becoming stable lead. Uranium is also extremely rare. Being a very large atom, it forms less frequently in supernova explosions. Specifically, in the universe, for every trillion atoms, there exists just one uranium atom. Crucially, uranium is not always exactly the same. Its nucleus always contains 92 protons, but its neutron count can vary. These are called isotopes. To differentiate them, we count their total protons and neutrons. The uranium produced by that primordial supernova divided between two isotopes, uranium-238 with 238 nucleons and uranium-235 with 235 nucleons. Uranium-238 is the less radioactive of the two, with a half-life of nearly 4.5 billion years. This means that whatever quantity of uranium-238 you possess, in 4.5 billion years, half will have transformed into lead through successive decays. But through these various decays, uranium-238 first becomes uranium-234, which is highly radioactive, with a half-life of 245,000 years before becoming lead. This means that when you have uranium-238, it always contains some uranium-234. Finally, we also find uranium-235, which has a half-life of 700 million years. In the nuclear industry, uranium-235 is what is interesting. Why? Because it is the isotope that fissions when bombarded with a neutron. The problem is, since it normally represents only 0.72% of natural uranium ore, you must first increase its concentration to make it usable. That process is called enriching uranium. At the end of enrichment, you have enriched uranium on one side, containing more uranium-235 that reacts better in nuclear reactors, and on the other side, depleted uranium, from which uranium-235 has been extracted. When that primordial supernova exploded, it distributed its uranium throughout the gas cloud that would later become the solar system. That is why, wherever you search, the ratio between uranium-238 and uranium-235 is essentially identical. In all deposits worldwide, natural uranium ore always contains exactly 0.72% uranium-235. Even in rocks brought back from the moon's surface by the Apollo missions, the uranium found there always contains precisely 0.72% uranium-235. It is a constant at the solar system scale. And so we return to Pierre Lat, where the factory spectrometer indicates 0.7171% uranium-235. There is a problem. First, they verify the spectrometer, but no, it is functioning properly. They test other samples and discover several behave identically. They then check whether this stems from a factory error that contaminated the uranium hexafluoride with spent nuclear fuel. But no. Investigators from the Atomic Energy Commission decide to trace the origin of the uranium. From Pierre Lat, they trace back to Malvezzi, where it is processed as tetrafluoride, then to Gugnon, where it is processed as uranate, called yellow cake. But invariably, samples showing low uranium-235 content all seem to originate from the same company, COMAUF, which operates 2 uranium mines in Gabon, at Monana, and at Oklo near Franceville. Investigators travel to Gabon and quickly discover the incriminated ore is extracted from the Oklo mines. There, they perform new measurements revealing rates below 0.5%. Between 1970 and 1972, from the 700 tons of raw uranium processed at the Monana facility, over 200 kilograms of uranium-235 are missing. Investigators initially think they have encountered natural uranium enrichment. But if they have found depleted uranium, where is the enriched uranium? COMUF closes the mine zone that produced this strange ore, and an international team of researchers and specialists begins surveying the area. Very quickly, they discover that if this ore is so poor in uranium-235, it is because it is not simple uranium ore. It is nuclear waste, but not waste dumped there by some careless power plant. No, this nuclear waste has been there for a long, long time. It is fission waste from a nuclear reactor sleeping beneath the rock for nearly 2 billion years. And very quickly, researchers discover there is not just one reactor, but 16, plus another 30 kilometers away at Bangomba. But until today, no others have been discovered elsewhere on Earth. Now, before explaining how we discovered these nuclear reactors and knew they were reactors, I need to explain how to operate a nuclear reactor. But do not try this at home. To operate a nuclear reactor, you need uranium-235 in sufficient concentration. But enriching uranium alone is not enough. The neutrons released during fission are too fast to reliably hit other nuclei, so you need a moderator. The moderator is hydrogen, and hydrogen slows neutrons just enough that they can strike other nuclei. Hydrogen is present as 2 atoms in every water molecule. You must therefore immerse your uranium-235 in water. Crucially, you must immerse enough of it, because neutrons fly off in all directions. To have a reasonable chance that one neutron will by chance strike another nucleus, you must place enough uranium in its path. A reactor must therefore contain sufficient uranium-235 concentration, be large enough, be immersed in water, and finally contain no neutron poisons. In reactors, poisons are elements that absorb neutrons and stop the chain reaction. Boron is one such element. At Chernobyl, massive quantities of boron were dumped onto the ruptured reactor to smother it. If you have enough uranium, rich enough, immersed in water with no neutron poisons, it sounds simple. But there is a problem. That 0.72% figure from earlier matters. If you just make a pile of uranium ore, the uranium-235 content is so low that a reactor will never go critical. We must go back in time to just after the solar system formed to understand why. Uranium is extremely rare in the universe, but it has an important characteristic. It is lithophile, which means it likes to associate with the minerals that make up most rocks. At Earth's formation, when our planet was still a molten magma ball, the heaviest elements like iron and nickel sank to the center and formed the core. Other heavy elements moved too, but because uranium prefers rock, a substantial portion remained in the solidifying crust. The material that sank toward the center continues slowly disintegrating, and the heat from those disintegrations helps keep the core hot. Earth, in that sense, is a gigantic nuclear reactor. So, approximately 4 billion years ago, uranium was dispersed throughout the crust, mixed with other minerals. Then a decisive event arrives in our story: the appearance of life. When I say uranium was dispersed, I mean there were no concentrated deposits yet. In the same period, give or take a few 100 million years, life appears on Earth. About 3.5 billion years ago, cyanobacteria appear, often called blue-green algae. They can range in color from green to purple. But what matters is that they live by photosynthesis, like modern plants. Photosynthesis takes carbon dioxide from the atmosphere, keeps the carbon, and releases oxygen. For billions of years, life on Earth was essentially blue-green algae releasing oxygen. That is how the oxygen in our atmosphere appears, because before that, there was essentially none. About 2.2 billion years ago, oxygen levels rise enough for something interesting to happen. Uranium exists within minerals, and when those minerals sit in water that contains dissolved oxygen, the uranium oxidizes to uranium dioxide, and uranium dioxide is soluble in water. Over hundreds of millions of years, water will wash uranium out of rocks. But where water enters a reducing environment, for example in the presence of organic matter, uranium precipitates out. Organic deposits therefore concentrate uranium in one place over very long times, creating the first uranium oxide deposits. Microbial life oxidized the environment and allowed water to extract uranium from minerals. Organic matter then concentrated the dissolved uranium into deposits. That is impressive, but a uranium deposit alone is not enough to form a nuclear reactor, because uranium-235 is too scarce today. Uranium-235 has a half-life of 700 million years, while uranium-238 has a half-life of 4.5 billion years. That difference matters. To find twice as much uranium-238, you would have to go back to Earth's formation. To find twice as much uranium-235, you need to go back 700 million years. Go back another 700 million years, and you get twice as much again. Go back yet another 700 million years, and you double once more. So, 2.2 billion years ago, the first uranium deposits form. In that uranium, there is nearly 3.5% uranium-235, roughly matching the enrichment levels used in modern nuclear power plant fuel. This uranium, buried under dozens of meters of marine sediment, gradually became a form of sandstone over millions of years. Through crustal movement, these sediments ended up several thousand meters below the ground surface. Faults in the rock let water enter. and that water gradually washed the deposit free of possible poisons such as chlorine. Plenty of uranium, enriched in the isotope uranium-235, combined with water and the absence of neutron poisons. A natural nuclear reactor then started and sustained itself. After precise analysis of the Oklo deposit's composition, researchers determined these reactors ignited 1.95 billion years ago, give or take 30 million years. Using mass spectrometry, they analyzed the fission residues in great detail. And today we know not only that there were reactions with uranium-235, but also that these fissions produced plutonium from uranium-238. Plutonium was long thought to be purely artificial, yet the isotope fingerprints tell a different story. We did not recover the original plutonium because its half-life is 24,000 years. So what remains are its disintegration products. Given the quantities of those products, scientists could evaluate how long the reactors operated and estimate their operating duration. Hold on to your seat. Our oldest nuclear reactor still in service began operating at Besnau in 1969. It is slightly over 50 years old, and modern fuel rods are used only a few years before being changed. By contrast, the shortest functioning Oklo reactor ran for 150,000 years, and the longest functioning reactor ran for 850,000 years. Oldest comparisons put human reactors into a very different timescale. About 500 tons of uranium participated in the natural fission reactions, releasing an estimated 100 billion kilowatt-hours of energy. That is enough energy to power 1 million Tesla Model S vehicles, each driving 500,000 kilometers, or enough to power all of France for nearly 3 months. But spread over nearly 1 million years, that does not translate into large daily production. What do these reactors look like in the field? They appear as large, elongated lenses, very porous, with thicknesses around 1 meter and lengths of about 10 meters. They are found in sandstone, enclosed in a sort of clay gangue. The lenses are striking in the rock record. Repeated high-temperature water flow dissolved salts in places so extensively that the deposits are nearly 40% porous. In fact, the sandstone was so dissolved that the original deposit must have measured nearly 5 meters thick. By losing part of its compounds, the sandstone became a clay that surrounded the uranium and helped keep it in place. Porous structure preserved the uranium. During reactor operation, because of deep underground burial, pressure and temperature must have been close to what is found today in a pressurized water reactor, namely 450 degrees Celsius and 200 bars of pressure. If temperature rose too high, water became less effective as a moderator, and the reaction slowed. If the fission reaction decreased, temperature dropped, and water became a good moderator again, stabilizing the reaction. This is essentially how many modern nuclear reactors function, and water circulation also allowed the removal of neutron poisons. Thus, these natural reactors operated, sheltered from view, for hundreds of thousands of years until their uranium-235 was consumed, and its concentration fell too low to continue fueling them. A nuclear reactor produces waste, chemical elements manufactured during fission. Those with too short half-lives were not found. The others, however, exactly the same as our current nuclear waste, were definitely there. And it is this, and the low uranium-235 rates, that allowed researchers to precisely determine what happened and when it happened. Since all these elements are radioactive, dating a nuclear reactor is like carbon-14 dating a mummy. Then, during the following 2 billion years, erosion did its work and brought these extinct nuclear reactors near the surface, where they were discovered in 1972, 2 billion years after their extinction. The Oaklo region has the advantage of not having moved much during this period and that was not guaranteed. Think about it. We are talking 2 billion years, but Pangaea, the supercontinent that fractured around the time the first dinosaurs appeared, dates from 250 million years ago, 8 times less. So imagine the luck we had that erosion or continental movement preserved this location. In fact, Oklo's reactors and Bangombe's are the only ones we know in the entire world. Could others have formed elsewhere? Probably. But in regions where Earth has greatly evolved, it is unlikely we will find them. Especially since these reactors must be over 1.5 billion years old at minimum. Indeed, past that period, uranium-235 had already decayed too much, and its ore content was therefore too low to hope for a reactor igniting. After this site's discovery, a question arose. Nuclear waste management. Not the 2 billion year old kind, but ours. You have probably heard about nuclear waste burial and the problems it poses. Indeed, something remaining dangerously radioactive for millions of years. How do you store it and ensure it will not contaminate surrounding soil, or that someone will not stick their nose in it? Now, to prevent someone sticking their nose in, the solution is relatively simple. Bury it very, very deep. Why? Because anyone with technology to dig that deep into rock will have technology to build a Geiger counter and realize it is dangerous. However, burying waste deep underground does not guarantee water will not pass through and become contaminated before rising to the surface. That is where Oklo's reactors proved very interesting, because we have radioactive waste identical to our modern reactors that remained confined there for billions of years. While we worried about how to package nuclear waste so it does not move for 1,000 or 100,000 years, at Oklo, they remained confined not 1 million, not 100 million, but 2 billion years. That is why today we consider nuclear waste burial must above all occur in suitable soil, a stable geological layer, whose nature we know will keep it stable at least until the waste is no longer dangerous. Because yes, Oklo's reactor waste has naturally not been dangerous for a long time. And when I say a long time, I mean 500 million years before the Cambrian explosion, they were already no longer dangerous. Speaking of the Cambrian explosion, let's discuss that. Life appeared on Earth nearly 4 billion years ago. 500 million years later, cyanobacteria began producing oxygen. Another 1.5 billion years later, that oxygen enabled the formation of uranium deposits. But during all this time, life on Earth's surface consisted of unicellular organisms, bacteria. The first multicellular creature was thought to be 1.2 billion years old. Then, 535 million years ago, the Cambrian explosion began, a period of several million years when life suddenly complexified, giving birth to today's great living families. It would take over 250 million more years to see the first dinosaur ancestors arrive. And meanwhile, Oklo's reactors are 2 billion years old. So that is vertigo-inducing. But what is the connection? Not far away at Franceville, intriguing fossils were discovered. They are multicellular animals dating from before the Cambrian. I told you the oldest multicellular organisms were previously dated to 1.2 billion years. But these strange organisms resemble nothing known today. They represent evolutionary branches that went extinct very long ago. They were found in the same geological layers as the nuclear reactors. So, are they connected? No. That would have been very clickbait-worthy. But do not try piecing together reactors installed by an extraterrestrial civilization 2 billion years old. However, finding these fossils in a geological layer, we could date with such precision, thanks to the presence of natural nuclear reactors, allowed scientists to determine they were the same age. Ladies and gentlemen, before you are the oldest known animals that lived nearly 1.5 billion years before most animals appeared on Earth. We know this thanks to natural nuclear reactors that functioned autonomously, producing plutonium in processes like atomic bombs, 2 billion years before our species even conceived it possible. And that's mind-blowing. Science rocks. Now click on the video on your screen if you want more video like this.